Hello once again. So we're restarting the video because I forgot to hit record. So fortunately I caught that early on. Otherwise the backup would have been to download the Twitch stream. But the problem is that that's not as high quality. So might as if I since I got it early on, then we might as well do it. So again, what we're going to go over today is a little bit about shallow versus deep copy. Since we kind of went over it at the end of the last class, but I want to go over it more again today. Then we're going to talk about C, Dynamic Memory Allocation, Malloc, and free. Then we are going to start talking about virtuals and up and down casting. And I'm also going to throw in some more copy constructors as well, probably with the shallow versus deep copy stuff. Okay. So as I was saying, this is a program that I went ahead and wrote at the end of last class. And it's based on the program that we did last class. The last class we did that 3D array dynamically allocated that we then made it into a class, and we had the constructor, the structure, etc. This is like a simplified version of that. This version is one-dimensional only. And so we have our class array type, which has a constructor, which by default will make the array size 10 unless we pass in an integer that is the size of the array that we're making. That information is stored here in the size, and the pointer here is the one that's going to point to the dynamically allocated one-dimensional array. As you can see in the constructor, we go ahead and we declare that array, and then we fill it with just random numbers between 0 and 9, I think. And then we also have a print function just so we can see what's in the array. And then on main, we initialize rand, and then we make two arrays. And I do have a destructor, but I intentionally commented it out so that I can show you the whole shallow versus deep copy. Because if you notice, last time, we had a segmentation fault whenever we had a shallow copy and we had a destructor, and I explained as to the reasoning of that. I'll explain it again today in a minute, but first let's go ahead and show you the shallow copy, okay? And so in this program, I went ahead and just created the two arrays. I went ahead and print both arrays out, and then I go ahead and set the second array equal to the first, and with the naive attempt of trying to copy the arrays over. I go ahead and then update in one of the arrays, the new one technically, the index 0 to be 42. And so that is actually, because it's a shallow copy, going to affect both the old array and the new array, so A1 and A2. I go ahead and then print it. So if we go ahead and run that program, we can see that they're randomly generated. So you can see that both arrays are completely different. After this, I go ahead and set 42 on array A1, which we can see here, but we can see that it has a side effect of also changing the first index of array A2. That's because it's a shallow copy. Again, the shallow copy, what is the difference between using the asterisks and the arrow? The asterisks is, you're talking about like where in specific, because it's something we kind of gone over already. So these arrays here, or these objects here are living on the stack. They're not on the heap, and they're not dynamically allocated. So I access the members of the array, including functions or variables, using the member access dot operator. If these were dynamically allocated, then I would be using the arrow operator. That is because the alternative of doing something like a dot b becomes ab, but then that is only if A was dynamically allocated. If A is dynamically allocated and you want to use the dot, then what you have to do is you have to use parentheses like this, because of the precedence that the dot has higher precedence than the asterisks. Okay, so yes, that's as much as because I really want to move on. So okay, going back to this, I went ahead and run the program, and as you can see, I am getting this side effect that one of the arrays is modifying the other one. The reason is because when you're making a shallow copy, you are copying the pointer's value, which means that the class A1 and A2, they each have their own pointer, but they have the same contents because you're making a copy. And so they're both pointing to the same location in memory, to the same one-dimensional array. So that's a shallow copy. And so the question arises, how do we actually make what is a deep copy, which is where it's an entire new array? And so there's two ways. The most basic way is, first of all, don't try to use the assignment operator. Instead, go ahead and manually copy the elements into the new array. How would I do that? Well, I would literally have to write a for loop that is the size of the array. So I is equal to 0, a dot 2 dot size is less than, I is less than a dot 2 dot size. I++. Okay? And so once you do that, then you can go ahead and copy over the values of A1 into A2, because that's what we're trying to do. Okay, or vice versa, if that's what, you know, whatever you, which one you want to copy to. Okay, so here I'm doing what is known as a member-wise copy. So I'm copying every single element of the array one by one. And this, of course, will guarantee that this is a deep copy. Now, this only works because both arrays are the same size, because I use the default size. But if the, you know, if you're making a brand new array and you're trying to copy the old one into that, you got to make sure they're the same size, and you have to first allocate the memory. That, of course, is already done in the constructor in my case right here, so I don't need to worry about that. But if it wasn't, I'd have to take care of it myself. So if I go ahead and do that, semicolon. Oh, A1, not AI. Here we go. Let's see what else. Oh, I see. What I need to actually do .ar, yes, because I'm not trying to copy. A is an object. I'm trying to copy the array itself, so I have to put AR in front of that. Okay, so there we go. So as you can see, by doing that, I now went ahead and did a member-wise copy. So when I go ahead in the line beneath and change A1's R0 to be 42, it does not affect this one. Okay, so before it affected it. See, they both changed. Now everything else is still the same. It's just kind of shifted a little bit because of this two characters here. But so I did have a duplicate of my array, but it's truly a duplicate in the sense that they're completely independent of each other. They're copied, but they're independent. So I can change one of them and it's not going to change the other one. Okay, so that's a deep copy. Now, what if I wanted to use, so I'm going to comment this out and say, what if I wanted to still use this method? Okay, for this, you would have to overload the assignment operator, which is the name of this equal sign, right? We will learn that when we talk about operator overloading, but I think that is going to be talked about 2 or 3 weeks from now, because we have the test in the middle, right? So the test is next week. So we won't, I think it's right after the test, but I have to look at the calendar. But we will talk about how to do that using that line of code. However, for now, that is kind of out of the question. So what is one other way you can do it? Well, that's where I wanted to talk about the copy constructor, actually, because the copy constructor allows you to create an object and initialize that object with an older object's data. Okay, so you can write something of this form, A1 and A2 like that. Of course, in this case, I suppose we'll comment out. Well, we're already making the object here, so I'm trying to think of what I can do here. I guess I'll just make a third object. How about that? So I can leave this example, because otherwise I have to change the code, and I'd rather leave this for you to see. So right now we have this format that we use as a solution, but now, you know, what I'm going to do is I'm going to make a third array, RT, call this A3, and I'm going to make it a copy of A2. Okay, we'll do something like that. So this you might have never seen this before. You might be like, what is this weird system that I'm using here? Okay, this is what's known as a copy constructor. When you're making an object, you go ahead and write the object name, and then, you know, if it's an object that has a constructor that requires parameters, or there's a constructor that allows you to have parameters, you know you could do that, right? So for example, if I wanted to make array A3 size of 20, I know that I can do that. This will compile. In fact, let's just go ahead and run it just to be extra sure, right? So it compiles, you don't see anything, but if I was to go ahead and call out cout, well, here I'll just do A3 print for now. You know, I guess I might label it. Yeah, I'll label it, why not? That. You can see that it's a much bigger array because I set the size to be 20, right? So that you know that you can have multiple constructors. In addition to having constructors that just require like random parameters that you use to initialize stuff, you can actually pass an object of the same type that you're building an object of. So in this case, I can pass an array type to an array that I'm making, and with the purpose of using that as to make a copy of that data and make a duplicate object. So that is exactly what I would do if I did something like this. A1 here, okay? So what this is saying is make an object called A3 and make it a duplicate of A1. However, if I just run it as it is now, it compiles. However, I have the same issue as before. I have a shallow copy. I guess to prove it to you, I can, here, I'm gonna scroll this up here to do that before I change 42. So technically speaking, you know, if I run this, you'll see the same output. You'll see that A3 has 42 in it. But think about what I did here. First, I created object A1 and A2, right? And you can see here that A1 had a 5 here, okay? It had a 5 initially. And then I am making object A3 from A1, which means that A3 should have a 5 as well, right? Am I looking at the right one? Let's see. A1, A2, A1 has a 0, 7. Why is that? Oh, because I'm copying it over from this because I need a deep copy. So I guess to show you, just to make sure that you see what is happening, let me go ahead and call the print right here so you can see it, okay? So we'll print out A1. We'll say this A1 before assignment to 42, okay? So that will make it easier for you to see. So as you can see here, this is the contents of A1 before we assign 42 to it, okay? As you can see, there is no such 42 to it. And so this is what we are using, because we literally just used it, because the cout is actually after this line. We just used it to create A3. So if I went ahead and printed out A3 right here, we'll also call this A3. Well, that's fine. It'll just be right beneath it. You can see that A3 has the exact same content as A1, right? So the copy constructor is a constructor that you get for free. So it is there. You can see that I did not have to create a special constructor for that. It works. However, we have the same issue because we're using dynamic memory allocation, that it is making a shallow copy. You can see that because if I go ahead and change A1, you can see that A1 has a 42 now, but so does A3, right? So we have the exact same problem. So now we need to fix that as well in the copy constructor, which means we can't use the default copy constructor. We're gonna have to make our own custom copy constructor that allows for deep copying. And so what we need to do is basically just create another constructor. So how do you create a copy constructor? Pretty simple. It's the same thing as making any other constructor, but the parameter is going to be an object of the same type. So in this case, another RT object. I'm going to call this one the old one, okay? So this is now a copy constructor of the basically it's kind of like the default copy constructor as it is now. Well, almost, because technically speaking, what is happening here is we'll call this the AR object is getting old.ar, and then AR size is getting the old.size, right? So I think this is exactly what the default constructor would be, okay? Oh, I forgot an %. Okay, there we go. And by the way, you might ask yourself, why did I use const in front of it? Well, it turns out with the copy constructor, it passes it usually by reference. And so, you know, when you're passing by reference, it's risky because you might accidentally change something from the parameter. And so you put const in front of it. But as you can see, even though I was thinking of passing by reference, I forgot the %. So that's why I got that error. But the compiler was actually pretty nice. It literally told me, like, is that what you meant? I'm like, yeah, you're right. So I went ahead and added it, okay? So this is actually what the copy constructor is doing by default. You can see that it's copying the pointer and it's copying the size. This, of course, is the problem. We don't want to copy the pointer. We want to make a brand new array, and then we want to copy the data into it, okay? So even though this is not a good thing, I'm going to take this moment to show you how to use C memory allocation, because might as well throw it into this example. So even though I would say, yes, you would just want to dynamically allocate it using new and delete the new array, we're kind of gonna use the C Malloc to do it, okay? Just because, like, why not? All right. So what we need to do is we need to get rid of this line of code because that's the problem line of code. And what we need to do is we need to basically create. In fact, here I'll show you the new way, and then I'll show you the equivalent Malloc way. How about that? So you can have both. So the new way is basically the same thing that we have in the original constructor that we made. It's just that code. So this line of code is literally going to be the same. So we're just going to put it up here. But instead of having a for loop that puts random data in it, what I'm going to do is I am going to copy over the data, you know, member-wise, as I showed you before with the for loop. So ARI is going to get old.ARI. So that is going to copy the old data into the new array. And that's it. I think we're pretty much good. In fact, let's just run it with this format. Oh, we don't have a nest variable because I copied and pasted, so it's just called size. So, and also here, size. So as you can see now, A1 gets changed to 42, but A3 does not get changed. So we have indeed made a deep copy. Changing one of the arrays is not going to mess up the other one, or vice versa. Okay, so this would be nice. However, let me show you how you would do this with C memory allocation. Okay, so with C memory allocation, what we're going to change is this line right here. We're not going to use now the new operator. It turns out that C++ and C are very, very similar languages. In fact, for the most part, C++ is backwards compatible with C. So when they came out with C++, they were they were trying to get people to adapt the language. So they didn't want to reinvent the wheel. So they kept a lot of the C style of coding. In fact, they wanted to make sure that people didn't get frustrated. So they were like, we're just going to make everything that normally works in C work in C++. So people can still code how they like in the past, but now they get the extra advantages. And so that's how we'll slowly convert them over to C++. And of course, it's a little bit of an oversimplification, but that's kind of what they did. However, not everything passed over. For example, there are void pointers in C, which that isn't really a thing in C++. And there's a couple of other tiny peculiarities that did not copy over. But I'd say that like 99% of the code like translated over. So which means if you take C code, put in the right libraries, like, because C does not use like IOStream. They don't use IOStream. They have their own version of that, which is stdio.h, I think. And so that is the input-output library that C uses. And they don't use cout and cin. They instead use printf and scanf, I think, or getcar, different ways of reading input. For printf, the assignment went ahead and helped you how to learn that. So I'll just do a quick example of that. How to use printf is you go ahead and write the function. It's a function, and the parameters of the function is what you're printing. So if you want to do a hello world program, you would basically do that, printf hello world. If you wanted to print variables, what you do is you can just put the variable directly. I believe that would work, but that's not usually what you do, because when you're mixing like strings and variables, what you have to do is you put a comma and you put the variables. So like we have A1, let's say that we have we have A1, I'm confused here. Like A, B, and C are variables, okay? And what you do here is wherever you want the variables to print, so let's say you want the hello and then A to be printed out, is you put the % symbol and then you put a special character that represents the type of the variable. So for example, if it's an integer, I believe you can use I or even D. And so that will go ahead and print out in that spot right here. It won't print out the % sign at all. It's just going to replace this with the contents of A. Let's say that B was a string. You can print that out with S. However, C strings are different than C++ strings. So you may need to put in C_str to convert it into a C string, for example. And let's say that C was a float. Well, if you want to print it after this one, then you can put F. So this is actually, some people actually like this method better than cout because you can very easily format input. So like if I want to have this many spaces there, I can go ahead and do that. And all it's doing is it's literally taking these 2 characters and replacing them with the contents of this. And the order that these things are coming on are the same order that you're passing the parameters there. So that's pretty much how printf works. You can read the documentation for more information, but it's just like any other function on the library. You just look at the documentation, use it, and move on. So, okay. So anyways, the function that we need to use for allocating memory in C is called Malloc, which stands for memory allocation. Surprise, surprise. And so how you use this function is the end game is you're still going to get an address from the function, just like you get an address from new. But in this scenario here, what Malloc requires are basically, well, 1 or 2 things. What it needs is a number, and that number has to represent the number of bytes that it needs to allocate, okay? However, I say 2 things because technically speaking, if you're allocating an array, you need to do the math yourself of how many bytes you need for the total size of the array, okay? So I guess reality is Malloc just 1 thing, which is number of bytes, but you can think of it as 2 things: the type of what you're making and how much of it do you need, okay? And so in this case, this could work. Like I could just hardcode a number there and this could work. However, this will not be very portable between different hardwares, because if I'm trying to make a single integer and in my computer it takes 4 bytes, it doesn't mean that in your computer it's going to take 4 bytes. It could take 8 bytes or it could take 2 bytes. Like really old computers, I think at some point integers were only 2 bytes long or something. So it does not make it very portable. So there's another function in C that's very useful that is known as a sizeof function. This function, you can pass it in a data type and it will go ahead and see how many bytes it needs to create an object of this data type. It doesn't have to be actually a built-in data type. I could pass it in like ART itself if I wanted to make like an object of ART size or something. So you can pass it any data type in there and it will figure out how many bytes it needs. So if I was just trying, if ART was a single object, this would be enough. This would be more than enough to make a single object. In this case, because I'm setting size of int, what this is doing is it's creating 1 integer that is dynamically allocated, okay? However, in this special scenario, I'm making an array of them. So I'm going to multiply this. Let me put the multiplication symbol. Oh, because I'm not clicking. I'm clicking on the stream. The multiplication symbol. And then I'm going to put how many of them I want. And because it's an array of size, right? That size is how many integers there are in my array, which I think is 10 right now. So this is not the pointer or dereference operator, indirection operator. It's not that. It's literally a multiplication symbol in this scenario here. I am multiplying the size of how much an integer takes in memory times how many of them I need. Because like if, let's say an integer takes 4 bytes and I need 10 of them, well, it's going to be 4 times 10, which is 40, which is exactly how much memory I need. So that's how Malloc works, or at least how it would work in C. However, in C++, there's one more thing that you need. In C, this returns to you a void pointer, which means it's an address where the memory is allocated, but it doesn't tell you what type it is. It's just like it's literally an address. It's not associated with any data type. In C++, the compiler doesn't really like that. In fact, sometimes I think most of them will give you errors, but I might be wrong. So in this case, you can see that it says invalid conversion from void pointer to integer pointer. It is complaining. It is telling me. Well, first of all, it's telling me that I need to put in some parentheses here, or semicolons. But it is also telling me that it does not know how to do that conversion. Like, it is confused how to convert this void pointer into an integer pointer. So what I need to do is I need to explicitly go ahead and do that. So I can do it in many ways. I could do something like this. I suppose the C way, since I'm using C, which is int asterisk, and that will go ahead and take care of that. I could also use static cast or dynamic cast or even reinterpret cast if I wanted to. But the point is that you have to cast your pointer to the correct data type, okay? So basically, this line of code is doing the exact same thing that this line of code is doing. But this is the C way, this is the C++ way, okay? Now that we did that, if we were to run the program, you would see that it would still be working just fine. However, let's go back to the whole delete stuff. Because it is 202. This is 202. So anyways, 302 is at 4 p.m. So yes. I hope that you not actually thought this was 302. But anyways, yeah, moving on. So let's go back to talking about the allocation that I commented out. So I commented out the allocation because the problem that we had last class, and we would have now if I hadn't commented it out, is that when you make a shallow copy, your destructor runs when the object goes out of scope. And so in this case, we have two objects that were pointing to the same dynamically allocated array. The destructor would very nicely take care of deallocating the array for us. The problem is, the first one that would run would deallocate it, but the second one will try to deallocate the same array that we've already deallocated in the first one because they're both pointing to the same array, which is a double deallocation of the same memory, which typically will cause a segmentation fault. Not always. Some systems are like kind of just let it slide, but Linux is not one of them. Linux will like crash you immediately with the double delete error. And so that is why I had it commented it out. If I go ahead and uncomment it though, because right now I don't have any sort of shallow copy going on, I should be okay. Yeah, I'm okay. But if I was to go ahead and do this, which basically would undo the entire for loop thing that I'm doing here, I would see that I have a big segmentation fault based on the core dump, okay? So I'm gonna go ahead and comment that out again. So, the last thing I want to show you with this example is that technically the second to last thing is how to do the deallocation in C style. So in C++, we know we can do the delete with the square brackets and then set it to null to avoid dangling pointers. But how would you do the same thing using C? In C, there is no delete operator. Instead, there's a function, and the function is called free. And all you gotta do is call free, and then as a parameter, you pass the object, or pointer actually, the pointer you're trying to free. Like that. Now don't do both, because then you're doing the double delete again. But if I go ahead and comment this out again, and I run this, then I'm okay. In fact, if I go ahead and run Valgrind, that's how I really know that I'm okay. So you can see here that I have 0 memory leaks, but I do have 2 errors, okay? And so you might ask yourself, what if I have no memory leaks, why am I having these errors? And so it turns out that, yes, this is how you deallocate in C, this is how you deallocate in C++. However, it's a really, really bad idea to mix C and C++ allocation. What I mean by that is that if you're allocating memory with new, then deallocate it with delete. And if you're allocating memory with malloc, deallocate it with free. Don't mix and match, which is essentially what I'm doing here with the deallocation, right? Because I am deallocating stuff that I did with new and also stuff that I did with malloc. And so that is problematic. That is like opening the Pandora's box here and getting some really nasty errors, okay? So do not mix them. And here's the reason why people will mix them when they know both. With delete, if it's an array, you have to realize that it's an array so that you can go ahead and do that, right? With free, you don't need to do that. Whether it's a single variable or a lot of them, it's the same call. Like, it doesn't matter. Like, free will take care of you if it's an array or if it's a single integer. Like, it's good. And so because it's so nice like that, people prefer free because it's easier. However, well, they also prefer to use new because that's easier than using malloc because they're like, oh, that looks nasty. I tend to disagree. I'd say that neither one is hard. However, people will go ahead and use new because it looks easier, and then free because it looks easier. And mixing new and free is a no-go. So don't do it. You will get at some point, you know, like in trouble for doing it. And I mean in trouble, not like, oh, somebody's gonna be angry at you. I'm saying like really bad bugs will start to happen given enough time. So for now, I'm gonna go ahead and comment out the C stuff and leave the C++ stuff and hope that the error goes away. As you can see, it did. because I'm not mixing C and C++. Okay, so that concludes the C memory allocation stuff. Basically, I suppose, don't forget after you do your freeing to always set your pointers to null to avoid dangling pointers and that kind of stuff. Okay, and also now you've seen how to do the copy constructors. So the last thing, I said there's two things because there's one more thing, is I want to introduce what is known as the rule of three, okay? And I know rule of two is like the whole, there's always an apprentice and a master for Star Wars, so it is not related to that, as much as it would be cool if it was. But rule of three is actually, has other nicknames. I just opened the Wikipedia to remember them. It's called the law of the big tree, or the big tree in general. And I'm going to go ahead and post the link for the Wikipedia in case you want to read about it. But, which you really should, frankly. What it's saying is that whenever you are using in code, whenever you have to create your own destructor for a program, or whenever you have to create your own copy constructor, or whenever you have to make your own copy assignment operator, okay? Whenever you have to do any of these, and by that, of course, I'm saying with the upper overloading with the assignment operator, which you haven't talked about yet, but I told you it's possible to do. Whenever you're messing with any of these, then you always need to mess with the other two. And the reason for this is simple. When you're dealing with dynamic memory, it's typically when you're dealing with a destructor, which means that if you had to modify what it would be like the default destructor for a class, it means that you're dealing with pointers and dynamic memory, which means that you're going to have problems with shallow and deep copy. Furthermore, you're going to have problems that, like we saw with the whole delete, that because we did a shallow copy, we are potentially calling delete on the same spot twice, okay? Those problems will, of course, happen with the assignment operator, as I showed you, and will also happen with the copy constructor if you don't overload it, as I showed you, okay? And so, not overload, override it, sorry. So it's basically saying that as a way to be safe, whenever you're dealing with dynamic memory, which means you're messing with the destructor, you probably want to also modify and create your own copy constructor and your own copy assignment operator, okay? It's a thing to be safe. It's actually something that will help avoid bugs, okay? There are also things like rule of 5 and whatnot, but that's kind of beyond the scope of this course, but it's basically meant to protect you. Again, if you're writing a destructor, it means you're probably dealing with dynamic memory, which means that you can potentially be dealing into a lot of problems, okay? As an example, when you're passing an object by value to a function, you may be inadvertently doing some sort of shallow copy, and you might modify that object in the function thinking it's a copy and not being worried about what's happening to the original one. But because it's a shallow copy, you're actually messing with your original object, and you may run into problems. Or not even if you don't mess with it. I've seen this happen in the first assignment in 302. If you pass an object to a function that has a situation with destructors and you're doing shallow copy, and then the object is using the function as a parameter, it just, you have it in your parameter on the top, then when the function ends and it deallocates any memory that might be there and runs a destructor, it's destroying the original object because of your shallow copy. And then when the destructor runs in main, where you call the function, you will get a segmentation fault, okay? So how would you solve that? Again, with the copy assignment operator and copy constructor being basically overloaded or overwritten to avoid these problems, okay? So just FYI, when in doubt, when you have problems, and the first thing you should see is think, do I have a destructor? Okay, I do. Then I need to go ahead and mess around with at least the copy constructor, and ideally also the assignment operator, okay? That's the end of that story. Okay, moving on. So now I would like to ask you guys, because I don't remember, have I talked about multiple inheritance and the diamond problem? Yes or no? Because I don't remember, honestly. Like, I know I talked about it in the summer for 202, but I don't remember if I talked about it already. And and if I did, I probably said I would finish talking about it later, but I want to know if at least I introduced it. So let me know. Yes. Okay, so I did introduce it. Perfect. Cool, cool, cool. So I will come back to that. But before I do, I'd like to show you some... then if I did talk about it, then I hinted at the solution, and I said that you could use this keyword called virtual to solve the problems, right? So that is something that is going to be the focus of this week entirely. Okay, I'm glad that I did. And don't worry, if you don't remember too well, it'll at least come back to you. That way I don't have to talk about it from scratch, okay? But all right, so virtual functions and virtual in general is a topic that I was just talking about with another of the professors in the higher level classes. People seem to struggle a lot or forget, or some instructors don't seem to be covering it enough. And so this semester, we want to especially make sure that we spend extra time talking about virtuals, to the point that from now on, starting not with assignment 6 or 5, the Inspector Gadget assignment, not with that one, but the one after, we are going to require you to write small reports of the code that you write as a reflection of the program, to better understand, see if you understand the concepts. And also, we're going to make sure that the virtuals are used in the remainder of the assignments to really, really nail that down, because that's the number one complaint that we're getting from the higher level classes that people are not understanding. It's virtuals and abstract classes and that sort of concept, okay? So, to start off that discussion, let me go ahead and introduce to you up and downcasting, because we can't really understand virtuals until we understand what up and downcasting is. And from there, we will go back into the multiple inheritance, because that was the other thing, by the way, inheritance. So virtuals and inheritance were the thing that most people struggle with in the later classes. So we want to make sure that we reinforce that. And that's literally like the best example is diamond problem, because it has multiple inheritance and virtuals in it. So yeah, okay. So first of all, let me go ahead and create a class A, and maybe a class B, yeah. In fact, let's make a class A called Dad, and class B called Son. Okay? And class B, or class Son, I suppose, is going to inherit from class Dad, okay? And remember, you have to write the keyword here, public, to inherit publicly, if that's what you want, which probably it is. And so now in this function, we're gonna create a variable x and a function foo. Int foo, or just void foo. And we'll just make foo basically cout x, okay? That's just a simple function. In fact, maybe end line after that. Okay, so now for the class Son, what we're going to do is we are going to have another variable. So we first start as a public class, and then maybe like add a y to it. And then we are going to write another function foo, but this one's going to cout x and then also cout y. Okay, I got so many semicolons there for some reason. All right, so now that we have those two functions, I think that we'll leave it be like that. We'll throw some dynamic stuff in a minute, but let's just let it be like that, okay? So let us go ahead and create some objects of this class, these classes. So first of all, let's go ahead and create an object of Dad, which we'll call D, and Son, which we'll call S, okay? And then maybe just call out the foo function from both. In fact, also, by the way, I guess, so it has some useful data. Let's initialize these, maybe like x is equal to 5 and y is equal to 9, okay? Just so it prints out, otherwise it's going to be 0, we won't know where it's coming from. All right, so now let's go ahead and call d.x, or not d.foo, how about that? All right, and then s.foo. Okay, so let's go ahead and run such a program and see if everything is good. We get a billion. Oh, first of all, I forgot these semicolons here. That is probably causing a lot of errors. And then I think everything else might be okay. So we'll see. What is happening? Oh, probably because of the assignment. I need to compile with C++11. And now, why am I getting so many errors? Cout is not a type. Did I not include IOStream using namespace std? Oh, ooh, I don't know what I'm doing here. I did not put the body of the function. I put parentheses for some reason. So ignore that. I have no idea what I was thinking there. In fact, probably because I didn't space things nicely. But the reason why I was trying to crush this is because we're going to run out of space pretty fast. So here, let's just make sure it's working now, and then, yeah, okay, it's working now. So now let's just go ahead and crush this up again so that we don't run out of space. Okay, like that. Cool. So it compiles, and if we run it, we can see that even though son is inheriting from dad, the function foo is being overwritten by the newer and upgraded function foo, right? So when we call d foo, we're getting just 5. When we call s foo, we're getting 5, 9. That's exactly what we want. Now, if we did not have the new function here, then both of these will just get 5 printed to them, right? See, 5, 5. Okay. So, but of course, you know, and y exists, but it's not being printed. So that's why we're overriding it, because now we have 2 variables. Okay. Cool. All right. Everything is as expected. No problems there. Let's go ahead and make things a little bit more interesting. Let us go ahead and make D and S both be pointers, okay? And so because they're pointers, we're going to dynamically allocate them by saying new dad and new son. And now, since that was a question early on, this is a good review. From this, because they're pointers, it becomes an arrow. So there you can see the difference of something from period becoming an arrow. Alternatively, we could also use the asterisk here, but that would make this have higher precedence, so we have to put this in parentheses, okay? So either one would work. I guess I'll leave them both because it's a good refresher of that, okay? As you can see, everything is still working okay, no problems. But now, let us talk about casting and up and down casting. Suppose that I make a third object, or a third pointer, okay? We're gonna make a pointer called fake dad, okay? Fake dad, or fake D, is just a pointer, and guess what? We are gonna make that pointer point not to, because I mean, if I do this, in fact, if I just go ahead and make it point to S, you know, that is just making both fake D and S point to the same thing. So I could go ahead and do fake D gets foo, and I would get 5, 9 printed, right? Or did I? See that? So if I went ahead, I guess I kind of went a little bit ahead. But if I make fake dad point to a dad, I get a 5. But here's the problem, which you kind of saw a little bit earlier because I typed the D there. I am making a pointer of the type dad point to an object of the type son. And son is a child of dad, right? But I'm pointing at him with a pointer of dad. So I am fooling the compiler in a way into thinking that the function foo that I'm calling here should be the dad's foo, because what kind of pointer is fake D? It's a pointer of that type. However, even though it's a pointer of that type, it is pointing to an object of son type. And so the compiler is like, oh, okay, well, what kind of, because remember, I just said, you know, in C, you know, you have void pointers and everything. But in C++, all the pointers are defined of what they point to. Fake D is a pointer of that. So it's pointing, it should be pointing to object of that. So it's like, well, I guess I'm going to call the foo from that. But it's technically wrong. It is technically wrong because it should be calling the function from the child. So how would I fix this kind of situation? Well, one way, of course, I guess the easy way would be, well, don't do it. Make the object not be an S. If I change from this dad to be son, then I don't have any problems, right? That is great, but it actually turns out that there are some situations where it might be useful to have a pointer that is of dad pointing to a child. And I'm going to show you lots of examples of that, probably not today, but next class. The question then arises, how do I fix not fooling the compiler? Well, this is where virtuals come to the rescue. So I'll show you the solution first, and then I'll explain why that's the solution. So if I go ahead here and put the word virtual in front of foo, and I run this program again, it is now fixed. I'll do before and after. Let's get rid of it again. Compile, run, we have the problem. Put the word virtual back in, compile, run, problem fixed. See this? It's like magic. With virtual in front of the foo, all of a sudden, the compiler is not fooled. The compiler knows, it knows which object it's really pointing to. It's like, yeah, okay, fake D is a dad pointer, but we know, the compiler says that, we know that it's actually pointing to a son. Like, it knows. So it actually calls the right function. So yes, it is indeed witchcraft. And this witchcraft is brought to you by the magic of compile time binding and runtime binding. So let me go ahead and write those terms on the iPad because they're kind of important. So normally in C++, when you've been coding until now, before your usage of the keyword virtual, whenever you're coding, you've done what is known as compile time binding. What this is that at compile time, as the name implies, all functions are connected to the class that they belong, okay? So like, your classes, your objects are made up of two major components, right? They have variables and functions. So like if I have a class A, I can have a variable or I can have like a function, right? So that is usually what classes are made of. Unless you're using a static variable, all the objects, variables, all the member variables are unique to their own object. So like if I make an object A1 and an object A2, they both contain an int x in them. Okay? They both have their own, because if you make two objects of the same class and they share a variable, then that would be problematic, right? So like if you make an object called, if I make a class called rectangle and they have length and width, and you have rectangle 1 and rectangle 2, you want them each to have a length and each to have a width, right? And so that is how classes work in C++ with member variables. Now, I did at some point talk about statics. And so with statics, that is a shared variable. So as in like every class shares one variable, right? So it's kept somewhere else in memory, and then they all have a reference to it that's just basically pointing to the same one, okay? So that's how statics work. Functions work kind of like that too, because it would be pointless to have the function written like 50,000 times in code. You can think of it like a little table of functions per class where foo lives. And so all of these have a pointer per se that point to that function. So if you ever call the function foo from whichever object you call it from, then it will basically call the one copy of foo that you have in code. And this is for efficiency purposes in general, because like, why have the code foo like 50 billion times? Your programs will be bigger, Warzone will be like 20 terabytes instead of 1 terabyte, okay? So essentially, that's one of the reasons why. So this association that is happening here is done at compile time normally in C++, okay? However, the problem of doing compile time binding with the example that we were running here is that, so this example here is that even though you as a human being can look at this code and see that this is really pointing to a sun, the compiler doesn't know. Furthermore, even you wouldn't know if I put an if statement here. If I said like, if I change this code to say something like, you know, int x, we're gonna set that to 0, and then cin x from the user, and if x is greater than 0, go ahead and, first of all, let's make this pointer before like that. So let's make just a pointer, but not pointing to anything. But then we're gonna say that if x is greater than 0, then fake d is going to get s. Otherwise, fake d is going to get d. Okay? So essentially, what I'm saying now in this piece of code is that based on the user input, if I put in a number that is positive, then I'm going to make fake d point to a sun. If I put a number that's negative, fake d is going to point to a dad. Okay? So let's actually run that, see if it works. So let's put a 5 in. If we put a 5 in, we can see that it is pointing to a child object. If we put in the -5, it is pointing to a data object, so we only get the 5, right? This works because it's virtual, but if I didn't have virtual in both of these scenarios, I would just get a 5, right? So the same issue. But so now what I've done here is not even you know at compile time which function it should call. It is only at runtime when this line of code runs and we actually can see what's in X that we know what it's really going to point to. So when you get to this line of code, like you have just no clue. Like I have no idea if this is a son or a dad because I don't know what the user is going to enter at runtime, right? So it is impossible because of this to be able to do this association at compile time, right? To be able to know who to link this function call to. And so virtuals come to the rescue. Virtual functions come to the rescue by allowing you to do what is known as runtime binding, which is the other term that I was saying. Runtime binding, and it's a complicated process, but in an oversimplified version is that it keeps a special table that is known as a V table. Okay? And that V table keeps all of these functions that are known as virtual functions, okay? Because you put the keyword virtual in front. So there is foo is stored there. And so now when you're making your objects and you're trying to figure out who to link foo to, in this scenario, it instead links to the V table. And so in the V table, it says, it's going to be a function from here, but I don't know yet. And so at runtime, it's looking in that V table for foo, and it knows what object you belong to. Internally, it remembers that. And then that's how it knows that to call the sun in the case it's the sun, or that in the case if it's that. Okay? Bit of an oversimplification, but you talk about it in depth in compilers, really. And also in a little bit in 326, CS326, which is programming languages. Okay? Because it's actually rather complicated process how we can achieve this. But the one more thing I would like to say about that, and I need to pull up the book for this because I don't remember, is there are other nicknames for compile time binding and runtime binding. I believe it's like dynamic and static binding, but let me Control F the book. That's the DS Malloc book. Compile time binding. Here we go. Static binding. Yeah. So compile time binding has other nicknames. Those are, here, I'll put them down here. So compile time binding is also known as static binding because I suppose the word static means it doesn't change ever. So, you know, it's always going to be that call, no matter what the object is, which would cause problems. Also, another nickname for it is early binding, I suppose because it happens early, I guess, because it's a compile time. And then for runtime binding, which is the other scenario that you get thanks to virtual functions. Is runtime one word? No, it's two words. Cool. Runtime binding. The other two ways that you call runtime binding are dynamic binding, which is kind of like the matching term for static binding. Think of like dynamically allocated variables that are done at runtime. In fact, dynamically allocated variables could also be called runtime allocated variables, I suppose. And also, I suppose to match the early binding is late binding. I don't ever really use early binding and late binding, but I do seem to sometimes use dynamic and static binding now that I remember it, actually. So yes. But yes, essentially, C++ corrects this problem by the mechanisms provided in virtual functions, okay? So again, this means that this is happening, you know, the linking of the functions happens at program execution, okay? Not at compile time. So we have a question. Would this same thing work if we put virtual on the song copy of foo rather than that copy of foo? So when you use virtual, this is a good question, by the way. When you use virtual, it propagates down. So if I use it on the parent class, it propagates down to any of the inherited classes, which means that foo will always be virtual. If son was inherited by grandson, it would also be virtual. But it propagates down, but it does not propagate up, which means that you would cause I believe it would still have the same issue if you did it the other way around. We can test it actually. But I believe that it will not propagate up. So this is 5 and then -5. So in this case, it's actually it is going up. Well, I stand corrected, I suppose, that it works up too, but I was under the impression that it does not. So be careful about that. We can see that this example works, but this is by no means an exhaustive proof, so be careful. I've been taught to put it on the parent of on the superclass, the biggest class, the most parent class possible, to avoid issues. Yeah, so be careful about that. I would still use it my way, but it worked in this specific scenario, so yeah. See, that's a sketchy one. I would not trust it. I would leave it like this, but you saw it worked. So good question, good catch. All right. So anyways, you still should be asking yourself why would do such a thing, right? Like this whole mess right here. And don't worry, like there are legitimate reasons as to why you would want to use this whole shared parent class and virtual stuff. Like there's a big legitimate usage of this, which is polymorphism actually. But we're not there yet. That's next class. Before that, what I do want to talk more about today is up and down casting again. It turns out that when I'm making fake dad pointer point to a son pointer, I am casting the son pointer to the dad pointer, right? So I'm casting a child class into a parent class. The act of doing that has a nickname of upcasting, okay? So let me write that down. In fact, I have a little reminder here because I sometimes have been known to mix up and down casting. So I have this little reminder here that I will go ahead and post here. So upcasting is casting child to parent. It is also possible to cast a pointer of a parent to a child. Okay? How would I do that here? Well, suppose that I have my fake D pointer and I'm going to make yet another pointer of the son type. I guess I'll call it real son in this case. If I go ahead and real son gets fake D, this is technically downcasting because I have a pointer from a parent class that I am casting down to a child, okay? However, if I try to compile it, I get an error. It says invalid conversion from dad pointer to son pointer. Turns out that downcasting is a very dangerous thing to do. Upcasting is okay because in the worst case scenario, if we got rid of the virtual thing, right? If we got rid of virtual, we know that the functions in the dad class are only calling the variables that are in the dad class, right? The functions in the son class could call either of the variables from son or from the parent that it inherited. So think about it this way. Suppose I have an object of dad and I'm casting it to an object of son, which means that I could potentially call functions that exist in son but not in dad, which means that I could access variables that exist in son but not in dad. So all of a sudden, I have an object that is of dad type, but because I fooled the compiler into thinking that it's a son because of the downcasting in this case, I could try to access like the y, so I could try to access y in an object that is of dad, and dad has no y, which can cause issues because now you're accessing who knows what. Potentially, what would happen is normally your variables, the order they appear is going to be like sort of like an array in a way. So like the first variable is at like address 0, then address 1, and so on. So what ends up happening is you're kind of going out of bounds. So that's kind of like the internals, but don't worry too much about that. Coming back to this, the big issue that we have here is that it's bad. And so C++ tries to stop you from doing it. But in this case, it's okay. Or at least it's okay sometimes, right? Because if fake dad is actually pointing to a son object, like it could be in the case of x being greater than 0, so like here, then it's okay. We had a dad, we casted it to a son, we had a son, we casted it to a dad, and now we're casting it back to son. That's okay, because it was already a son in the first place, right? But the compiler doesn't know that. The compiler thinks of the worst case scenario where you really had a dad that you're trying to cast into a son. So that's how you're getting this error. So how do we fix this error? Well, first of all, do you want to fix that error? Like, is this a safe thing that you're trying to do? But in this case, it is, at least some of the times. So you can use Dynamic Cast. Dynamic Cast is a type of cast that allows you to do this downcasting, or upcasting too, I suppose. And in this case, the type of the cast is a son pointer. If we do this and we compile it, it runs. And if I put a positive number, everything is fine. If I put a negative number, I think everything will be fine, but we'll find out. Yeah, everything is fine. However, let me go ahead and see out what the contents of real son is. It's like that. I'm not putting in an ampersand because it's a pointer. So I actually want to see the contents of the pointer. Okay? So like the address. Positive number, the address is some legit address, or at least looks legit. Negative number, address is 0. That's a red flag right there, because the odds of it being address 0 are pretty much none. Turns out that Dynamic Cast allows you to do this whole downcasting with a catch. There are 3 kinds of casts in C++. Technically 2 plus the 1 from C, but still. We have static cast, reinterpret cast, and dynamic cast. So let me go ahead and write them down. We have static cast, in which you would put there the type that you're casting to, and here you're taking the object, and probably a pointer, but I mean it could be, I guess, an object technically speaking in the case of static cast. An example of me doing that is like, suppose that I have a double double X and I have an int Y. Okay, and there's some data in them. I can go ahead and say something like static cast. Let's cast the okay, why not? I guess let's cast the double into an int. We're gonna lose accuracy, but whatever. So that will be an example of that. Okay. If you wanted to do this the C way, you could do it by doing kind of what we did earlier with Malloc. You could do this. I believe that would be how you would do it. Oh, and where are we saving this? We're saving it to Y, so. Yeah, I think that would work. I don't think you need parentheses around X, but if you did, just throw them in. Kind of what we did with Malloc. But the bottom line is the way you do it in C. The top line is how you do it in C++, so with the static cast, okay? So static cast works for like normal data types, like built-in data types and whatnot. It also works for pointers, right? So like, if you wanted to cast a, it would be tricky to find out what it would work with a pointer that would be allowed. I think maybe downcasting, upcasting would work okay with it. Let me just let me test it before I tell you that. So technically speaking, here there's upcasting going on, right? We have the son going to the dad. So if I write the word static cast dad pointer to son, let's see if that compiles. I think it should, but we'll see. Yeah, it compiles. Okay, so that's an example where you could use static cast effectively with a pointer. So in this case, I have an object here, S, technically a pointer actually, and I'm casting it into a dad pointer. So this here is already happening automatically, so I didn't need it. That's why I had an S before there. But here I'm being explicit. Remember, the other one is coercion. That's implicit. Casting is explicit. And here I am doing casting, okay? So, because I want to be more explicit. So anyway, static cast is the first of the cast. The second one is the one that I'm doing with dynamic cast. Dynamic cast is the only way, other than Reinterpret Cast, but I guess the only good way of being able to do downcasting, okay? Because downcasting being very dangerous because of what I said with the whole dad to son, but not containing the actual, not really being a son object. Downcasting allows you to do that at a cost. And that is that it will do some checks at runtime to make sure that the cast is actually valid, okay? So in this case, again, you're going to put the type that you want to cast to, and you're putting this once an address or of the pointer that you're getting from. And if the cast is okay, if I have a son object pointer that I've casted to a dad pointer, and then I'm trying to cast it down again back to a son pointer, which will be the downcasting. If I do it with dynamic cast, it'll work, and as you saw, we get a valid address. However, if you're trying to do an invalid cast, such as if there's a dad pointer that is really pointing to a dad, and I'm trying to cast it to a son pointer, which will be really, really bad to do, in this case, dynamic cast will not succeed with the cast. It will actually, instead of returning the address of the pointer, it's just going to return 0. Okay? And that is why you see a 0 there. And that's a good thing, because then you can check that with like an if statement and see if that address is valid or if it's null. Because 0 would be the equivalent of null. And then you know that the cast failed, which you can then do error handling or whatever. Okay? So that's the dynamic cast. The third cast is the Reinterpret Cast, which I personally like to call the Yolo Cast. Because that cast is a C cast. It's a cast that doesn't do any checking. It's just like, you want it, you got it. You feed it in a bad downcast, it'll do it for you. Not only that, it'll literally cast anything to anything. Like I can cast a pointer of son or dad to like an integer pointer if I wanted to. Why would I do that? I frankly don't know why you would do that. I suppose I could show you an example of a little bit about a bad way of achieving a heterogeneous array that way. But it's probably not a good idea. However, I will show you this because it's pretty cool. I don't know if next time, but at some point, and if not, I'll just let you watch one of the summer lessons, where you can use Reinterpret Cast to cast a class that has private variables into an equivalently structured struct that has everything public in it. And it's an easy way to access private variables in a class, which is pretty cool. In fact, my old assignment 7, which was Crack the Vault, I believe it's assignment 7, I'm not sure, is about that. But of course, you guys are not doing that assignment because we're doing the shared assignments from all classes. So no hacking private variables in this semester, I guess. But yeah, I'll see if I have time to talk about it. But if not, I'll just let you watch that if you're curious about that. So anyways, that's pretty much it. So again, as a summary, up and down casting. Upcasting is what is known as casting a pointer of a child class into the parent class. And then downcasting is casting a pointer from the parent to the child, which you can only do with downcasting, okay? Or Reinterpret Cast, which again is the Yolo Cast. But you don't want to use Reinterpret Cast, because again, that's just like, there's no checking. It's like playing with fire, okay? It's like, you know, with great power comes great responsibility. Yolo Cast is like, you know, there's no checks. It's just like, whatever. You know, you only live once kind of thing. So if you crash, it's on you. So that's it. That is the class for today. So next time we will talk about virtuals more. Like, I'll give you a concrete example of a good usage of virtuals and a good usage of up and down casting. Maybe we'll talk about virtual destructors, virtual inheritance, and the diamond problem. And that will pretty much conclude the day. We'll talk more about virtuals as well next week. And then we'll have the test on Thursday or Wednesday. Thursday, I think, technically. Yeah, Thursday, right? Because we can do the review Wednesday and then have a test on Thursday. So, yep, that's it. So, cool stuff. And hopefully you learned. But if not, on Wednesday, I'll make this code available so you can play with it. All right? So until then, thanks for watching. And I will see you guys on Wednesday.